In this video, we're going to look at polynomial graphs where some of the zeros have multiplicities. So a zero has a multiplicity, which refers to the number of times its associated factor appears in factored form of a polynomial equation. We looked at this a little bit before, but when you have factors that show up more than one time, like if it was x plus 3 times x plus 3, that gets you the same x value, x-intercept. But what does that look like on the graph? Because it does actually look special. So we have, for a given zero, if the multiplicity is odd, the function f of x crosses the x-axis at that zero. It crosses it, and it switches from above to below, below to above. For a given zero, if the multiplicity is even, the function f of x bounces at that zero. It doesn't actually cross through, it kind of bounces off the x-axis. So let's look at some examples. So for an odd multiplicity, if that multiplicity equals 1, so this is really the most basic of multiplicities. Really, it's almost like no multiplicity. If an x-intercept, if a zero has a multiplicity of 1, then the line just goes straight through. There's nothing fancy. Whatever curves happen, it looks like that. But for a multiplicity greater than 1, that's odd. So for example, that would be like a multiplicity of 3. This is what we might see. So here is the 0 on the x-axis, and it kind of, we like to call it a snake. It kind of gets like flat on the x-axis for a second before it continues on the other side. You could see it on going the other direction as well. It could be going this way. It just kind of flattens out for a second before it continues through. Now an even multiplicity, a bounce, this would be like a multiplicity of 2 or a multiplicity of 4, you know, all the even numbers. And this is where it bounces off the x-axis and it does not actually cross. So if this was my x-intercept here, this would come up, touch it, oops, I don't want it to be a straight line then. It would come up, touch it, and then bounce back down. So it's like a parabola almost with its vertex at the x-axis. But, you know, we're dealing with polynomials, so with a polynomial graph, we're kind of putting it all together. So we might have, you know, up, down, up, and then a bounce right here. So that's what it would look like with a polynomial. So let's actually try some of these. Example 1, f of x equals x plus 9 times x plus 3 times x minus 4 squared. And right here, that x minus 4 squared. Remember, when something's squared, that means I'm multiplying it by itself 2 times. So x minus 4 times x minus 4. So the way that this is written with that exponent of 2, that tells me the multiplicity of this factor. So to find each of the zeros, we'll start with x plus 9. We set it equal to 0 and solve. Once it's in factored form, we can do that. X equals negative 9. Now, x plus 9 had an exponent of 1, so its multiplicity is 1. For x plus 3, set it equal to 0. X equals negative 3. Again, this factor had an exponent of 1, so a multiplicity of 1. And then finally, that x minus 4 factor, we get x equals 4. Now this one had a multiplicity of 2 because it was squared. Now before we're ready to put it on the graph, we need to determine the degree in end behavior. So the degree, when we're in factored form, we can find it by simply adding up all the multiplicities of our zeros. So we have a multiplicity of 2 plus a multiplicity of 1, now we have 3, plus another multiplicity of 1, that's 4. So this is a degree 4. And then the end behavior, let's focus on the leading coefficient before we fill in end behavior here. The leading coefficient would be positive. So we really just look in front of the first factor, and as long as there's no negative there, we can say it's a positive leading coefficient. So what that means here, for leading coefficient, positive or negative, we have a positive leading coefficient. This end will point up. Degree, even or odd, the degree is even, which means both ends will point the same direction. And now we're going to plot our zeros. So we have x equals -9. And then sometimes I like to just put a little number there so that I remember the multiplicity when I draw the graph. Then we have x equals -3, also had a multiplicity of 1. And then x equals 4 has a multiplicity of 2. So now I'm going to go ahead and connect the arrows. It's like a game of connect the dots. I can only go through the x-axis if it's an x-intercept that I already have plotted, and I need to draw the appropriate multiplicities like we saw before. So I'll start on the left. The first one has a multiplicity of 1, so I go straight through. The next one's 1, so I go straight through. And the last one is 2, which is a bounce. So we're going to touch it and then bounce off, and we'll touch the other end. And there is our graph. Now for end behavior, we were going to fill this out as x approaches infinity, that's the right side, f of x approaches infinity, and as x approaches negative infinity, that's the left side, f of x approaches positive infinity. Oops. Because both ends point up. All right, let's try the next one, example 2. We have f of x equals -1/2 times x plus 2 times x minus 2 squared. So for the zeros, now I know that we have this 1/2 out front, but because it doesn't have an x, it's not considered a zero. So we've got x plus 2 as our first zero. Set it equal to 0 and solve. X equals -2. And then x minus 2 is the other 0, set it equal to 0 and solve, and get x equals 2. Now the x equals -2, that one had a multiplicity of 1. And x equals 2 had a multiplicity of 2. Degree, the degree of this, well, remember we just add the multiplicities. 2 plus 1 is 3, which is odd. And then the leading coefficient, this time we're going to look right out here in the front. We have a -1/2, which means that our leading coefficient is negative. Before we even graph this, we could fill out the end behavior. So as x approaches infinity, remember that's the right side of the graph, and that depends on the leading coefficient, positive or negative. Because the leading coefficient's negative, then I know that f of x approaches negative infinity. Then, as x approaches negative infinity, that's the left side of the graph. That depends on whether the degree is even or odd. Because our degree is odd, that means the ends will point opposite. So this one we already knew was down. I just forgot to draw it. So the left side will point up so that they are opposite of each other. That means on the left, f of x will approach positive infinity. All right, now I'm going to plot my zeros. So we have one at -2, and that one has a multiplicity of 1. And then we have one at +2, and that one has a multiplicity of 2. So I'm going to get started here on the left arrow, go through the first x-intercept. All right, I'm going to touch the second one, but it has a multiplicity of 2, so that's a bounce. And then go to the other end. As long as your multiplicities and end behavior are correct, you should always end up on the right side of the arrows that you're trying to connect. Okay, so make sure you're not going through the x-axis at any other points. If you need to, then you need to erase and find your mistake. Example 3 here, I've got x minus 6 is my first factor, so I'm going to set it equal to 0 and solve. X equals 6, and that one has a multiplicity of 2. And then x plus 3 is the second factor, set it equal to 0 and solve. X equals -3, and that one has a multiplicity of 3. For the degree, we're going to add the multiplicities. 3 plus 2 is 5, which is odd. And then the leading coefficient for this one, if we look out front, I don't see any signs, so that means it's positive. So for leading coefficient, positive or negative, that one's positive, so we'll point up on the right side. And the degree being even or odd, it is odd, which means my ends will be opposite, so the left side will point down. Now my zeros, I have one at x equals -3, and that one has a multiplicity of 3. And then I have one at x equals 6 with a multiplicity of 2. So now we're going to play our game of connect the dots. Starting on the left, I'm going to go up to this first x-intercept, and this one has a multiplicity of 3, so that's the one that kind of snakes. We kind of go flat, but we continue through to the other side of the x-axis. And then we're going to go over, this next one has a multiplicity of 2, so that's a bounce, so we'll bounce off, go to the other arrow, and there's the picture of our graph. For example 3, I'm going to let you fill in the end behavior on your own, and you can check the answer key if you want to check your work. All right, so now we're going to write polynomials from a given graph. So if we already have a picture of the graph that's been drawn, can we actually write the function or a factored form of the function that might be what we're looking at? And of course, there's different variations to graphs that have the same zeros. We're just going to write one possible variation. So first, I'm going to list the zeros and the multiplicities that I see based on the graph. So we have a 0 at x equals 2, because that's this x-intercept here, and we're looking at the x value. And that one, I notice that its multiplicity has to be even because there's a bounce. I'm just going to say it's 2. You could do a bigger number, but I'm going to go with 2. Then we have another 0 over here at x equals -3, and notice it just goes straight through. So that means that x equals -3, its multiplicity is 1. Based on the two zeros and multiplicities I've written, let's find the degree. We have a multiplicity of 2 plus a multiplicity of 1 is a degree of 3, which is odd. And that matches what we're seeing on the graph, because if you notice, our ends are pointing in opposite directions. So that is what we'd expect if it was an odd degree. Now for the end behavior, real quick, as x approaches infinity, remember that's the right side. Where does f of x approach on the right? It is pointing down, so it's pointing towards -infinity. What does that mean though? That means that our leading coefficient for this equation must be negative. Then on the other side, as x approaches -infinity, f of x is approaching positive infinity. We know that's true because the degree is odd. So now I'm going to put it all together. We have got f of x equals, first we need the negative leading coefficient, and now we need the factored form for these zeros. So we have x equals 2, but what would that look like if it was in factored form? And so for that, you can think x equals 2. If I want to move 2 back over with x, I could subtract it and get x minus 2 equals 0. That is the factored form. And maybe in your head, you could kind of think through that. So in your head, think if x equals -3, what is the factored form of this? It would be x plus 3. And there's the factored form. Now, if you were asked to write out an actual equation, not in factored form, you would just multiply these out. But today we'll focus on factored form. All right, for this next one, take a second, pause and try, and then I'll go through it with you. All right, so I see a 0 at x equals -3. And that one has a multiplicity of 1. And if you wanted to real quick, the factored form of this would be x plus 3. Next, I see a 0 at x equals 2. And that one has a multiplicity that's even. I'm just going to go with 2. But I know this is true because it's a bounce. And so that would be the factor x minus 2. Oops. I had a multiplicity up here and I didn't even put it. This is why teaching in class is good. You guys would correct me. Look, we have a multiplicity here of 2. We need to go back and put that on our factored form. So the factor x minus 2 was the one that had a multiplicity, so it should be x minus 2 squared. Now the x plus 3 had a multiplicity of 1, so that would just be to the first power, and we don't really need to write that. So here is our final answer. Let's try this next one. So this has x equals 2 is the 0. So in factored form, that's x minus 2, and with the multiplicity, that would be squared. Based on the degree, well, I have a degree of, oh, well, I'm not done yet. That's why I didn't match. We have x equals 5. That's our last factor. It has a multiplicity of 1, and its factored form would be x minus 5. Now I'm seeing I have a degree of 4, which is even. Both ends point up, which is what we expect. And I know it's a degree of 4 because I add those multiplicities. And for the end behavior, if I look, the leading coefficient I know must be positive because the right side points up. So when I put this together in factored form, I get x plus 3 times x minus 2 squared times x minus 5. And there's my final factored form.